So basically cathode rays are colorless, right? But how they have observed this? We have seen this thing as green color glowings, but those are colorless. How come the green color appeared at the cathode ray tube? Why we need to maintain this kind of a low pressure gas inside the tube? What happens if the gas is at a high pressure? What happens? Why we need a low pressure gas inside the tube? The question is why we need this kind of setup to prove that cathode rays are traveling towards the positive terminal. Why this is not enough? Why this setup is not enough to prove that cathode rays are traveling towards the positive terminal? Actually, this deviation, this direction of deviation can be predicted with the use of Fleming's left-hand rule. Cathode rays can ionize gases. These are some properties of cathode rays. Cathode rays can ionize gases. This deviation angle theta is actually proportional to the charge over mass ratio. Hello Lamai. Last day we have discussed about how that atomic concept came to the world, right? I wish you have gone through the session, right? So today we are going to continue with that thing, right? So ultimately we had came across the Dalton's theory and Dalton's four postulates, and then some evidences which ultimately made to prove those four postulates are wrong, right? Basically what went wrong with the Dalton was actually he didn't account of any charged nature of matter to its atom, right? So that there are a few evidences where the matter is interacting with charges, right? So we have gone through those evidences, the static electricity. Then we had discussed about how the electrolysis process occurs, and another evidence was actually electrochemical cell processes. You may have heard about that thing in your O levels, right? So those are some evidences where matter interacts with charges. That means to interact with charges, matter should have some charged nature, right? So that was not accounted with the Dalton's four postulates. That was the main reason that for Dalton's theory to fail, right? So with those experiments, basically carrying with those charges and the liquids, the electrochemical cell processes, electrolytic cell processes, scientists got to know that matter is with kind of relationship with charges. Then a scientist called Stoney, right, came up with a wonderful idea. It is like this. He said, okay, look, that Dalton said no, that matter is with a fundamental particle, that uncuttable, indivisible, right, indivisible particle called atom. That was what Dalton said no. So that I am saying that charge also should have such a particle. The charge should also has such a fundamental unit, which is no longer uncuttable, no longer indivisible, the ultimate unit of charge. There should be something like that. So I'll call that thing as electron. That is what Stoney said. So that's a very wonderful idea, right? That is the origin of the idea of electron. For charge, there should be a indivisible, uncuttable, fundamental, the smallest, tiniest unit. That is called as the electron, right? That is the first idea of electron actually done by Stoney, right? So today we are going to discuss about this electron, the fundamental charge carrier. right? So let's meet the electron, right? So first evidences of the electron is actually found experimentally by a scientist called William Crookes. William Crookes was the first scientist to see the electron first. Basically, he done some experiment with his apparatus called the Crookes tube, and he had seen some special kind of glowing inside his Crookes tube. Let's go to this video. I'll arrange some video which is actually done by those Caltech University lecturers and the students, right, about this Crookes tube. Let's go to that video and get some idea about this experiment and how the cathode rays and the electrons will behave. Let's go to that thing and then we'll continue the lesson, right?
Cathode tube is first invented by the British chemist and physicist Sir William Crookes. Therefore, it is also known as Crookes tube. This Crookes tube can be used to observe properties of cathode rays. Inside of these tubes contain a gas at low pressure. When observing electrical discharge, a significant voltage difference should be applied to two metal plates at both ends of the tube. Then, the negatively charged plates called cathode emits invisible rays which pass to the other end of the tube. This end is specially coated with fluorescent material which glows when these invisible cathode rays fall on it. Let's observe the properties of cathode rays. Cathode rays travel in a straight lines. When an opaque object like a metal cross is placed in the path of cathode rays in a discharge tube, a shadow with sharp edges of the metal cross is formed at the end opposite to the cathode. The placement of this shadow proves that the cathode rays emit from the cathode and they travel in a straight line, just as shown in this video. Cathode rays are affected by magnetic fields showing a deflection perpendicular to the magnetic field. The direction of deflection is similar to the deflection of any other negatively charged particles. Therefore, electrons can be concluded as a negatively charged particle too. Cathode rays are a beam of particles having mass and possess kinetic energy. On placing a light paddle wheel in the path of cathode rays in a discharge tube, the blades of the paddle wheel rotate. This was considered evidence that electrons have momentum. However, there is doubt on this conclusion as heating of the tube can also make the paddle move.
Right, you have went to the video, right? That is a little introduction about the cathode rays, right? Okay, let's discuss the processes happening at the cathode ray tube and have a clear idea what kind of scenario leads to those observations, right? That is what we are going to discuss here, right? Okay, this is kind of a picture about the Crookes tube, right? Crookes cathode ray tube, cathode ray tube, right? Okay, so you clearly see some high voltage is applied to some glass tube, right? Two terminals are there. The negative terminal is called the cathode and the positive terminal is called the anode. And here they have maintained a gas with very low pressure. A gas with very low pressure. Inside here you have a gas with very low pressure, right? So that was the experimental setup to observe the cathode rays done by the William Crookes, right? So when this setup was constructed, when they switch on the setup, right? When they switch on the setup with a very high voltage and a very low pressure, kind of a near vacuum, right? They have seen, Crookes and his teams has seen kind of rays, kind of green color glowings starting from cathode going towards the anode. They have seen such an observation, kind of green color glowings starting from cathode going towards the anode, right? Because they had seen these rays are starting from the cathode, they have named these rays as cathode rays, right? As they have seen these things are starting from the cathode, right? They have named these rays as cathode rays, right? So those are the cathode rays, right? So that was also mentioned in your video, right? So let's discuss a bit how you are able to see these things, these green color glowings, as the cathode rays are known as colorless stuff. These are colorless rays without a color. So basically cathode rays are colorless, right? But how they have observed this? We have seen this thing as green color glowings, but those are colorless. How come the green color appeared at the cathode ray tube? That is the first question that can be asked from this setup, right? Even though the cathode rays are colorless, how you were able to see them? How you were able to see them? If those are colorless, you can't see them, you can't detect them. How you were able to see them if the cathode rays are colorless? That will be the first question there can be there in your question paper, right? So another few questions can be asked. Let's try to come up with good answers for those. Let's try to come up with the answers, right? The next question can be asked is why we need to maintain this kind of a low pressure inside the tube. Why we need to maintain this kind of a low pressure gas inside the tube? What happens if the gas is at a high pressure? What happens? Why we need a low pressure gas inside the tube? Then only you observe the cathode rays. If the pressure is high inside the tube, you won't observe these green color glowings. Why is that? Right? Those are the main two questions that can be asked from this experimental setup of William Crookes, right? Can you answer those things? How we are able to see the cathode rays if the cathode rays are colorless? Yes, the cathode rays are colorless, right? Then how we are able to see them? How we are able to see this color, right? That green color, if cathode rays are colorless. Any answer? Yes, you have some opportunity to answer me, right? So why we consider how this color is produced by the cathode rays, even though those are colorless. Yes. So we have two students, right? Shevon. Any answer? Shevon මොන හරි හිතනවද? Or Hamid, right? Do you have any? No, right? Okay, let's discuss why these cathode rays, how these cathode rays are able to give these green color glowings. It is like this, Lamai. So basically, cathode rays are colorless, right? What happens is, right? So you have few gas particles inside your tube. Right, inside this Crookes tube, you have few gas particles, low pressure gas with low pressure. So gas molecules are there. Few gas molecules are there inside this tube. So what cathode rays does to those gas particles, gas molecules, is this. See, so gas. Let's consider a gas kind of helium or stuff. Helium. Let's consider you have helium gas inside the tube, right? Then what it does is basically this is the helium atom, right? I'll draw some helium atom here. This is the helium nucleus, right? This is the nucleus of the helium, and this is so its first energy level. This is its second energy level. So helium atom is with that 288 energy levels. No, the first energy level can have 2 electrons. Second energy level can have 8 electrons, like that. Helium atom is with energy levels, right? And there you have electrons, right? You have some electrons. This is kind of a helium molecule appearing inside the Crookes tube. So what will happen? So basically cathode rays are colorless, Lamai. Those will come. Cathode rays are colorless. Those colorless cathode rays come, and when those hit the electrons of these helium molecules, when these cathode rays, which are colorless, right, when they hit those electrons, they will transfer their energy. They will transfer their energy to these electrons to move up to a higher energy level, to increase its energy. The electron will grab these energies supplied by the cathode rays. When cathode rays are coming, those are with some the things are moving. That means kinetic energies are there. When those are coming, that kinetic energy will be transferred to these electrons, so that these electrons will move upwards to a higher energy level. With time, when these electrons comes back to the lower energy level by releasing the excess energy absorbed, the excess energy earlier absorbed, when those guys releasing that energy, if those things falls under the electromagnetic radiation region, when those falls under the under the visible region of the electromagnetic spectrum, it means spectrum, the visible region, you will see some color appearing. Basically, in this case, right, this radiation emitted by the electrons comes under the green region of the electromagnetic spectrum, the visible region, the green colored region. Green colored wavelengths are given. So that is why you were able to see some colors appearing. Not because of cathode rays are colored, the cathode rays are colorless, but the cathode rays are able to produce some glowings, produce some light emitting processes with the gas molecules inside the tube, as well as with the molecules, the atoms of the surface of the glass tube. So this could be a helium atom, or this could be an atom in your walls of your glass tube. So cathode rays are colorless. Those are able to produce glowings out from the atoms, inside the atoms of your gas, as well as atoms of your walls of your cathode ray tube. That is how the cathode rays are able to generate some green color from that gas as well as from that walls of your tube, right? Remember that. That is how we observe the presence of cathode rays. Not because of they are colored, but they are able to produce some glowings from the gas inside the tube, as well as from the walls of from the atoms of the glass walls of your tube, right? So that is the answer for the first question I have asked. That was actually, even though the cathode rays are colorless, how we are able to see those, right? Okay, I think you got some idea, right? Any questions regarding that explanation? So in ප්‍රශ්නයක් තියෙනවා ළමයි ඒ explanation එක ගැන, how the cathode rays are able to give you some colors even though those are colorless. Clear, no? We'll write these ideas, right? Then let's discuss why we need a very low pressure inside the tube. We need a very low pressure inside the tube. If not, we are unable to see these green color glowings appearing. So why we need such kind of low pressure situation, near vacuum? Why we won't see the production of cathode rays in a high pressure situation? Why we need a near vacuum? Why we won't see these things with normal atmospheric pressure? Why we won't see this thing with 1 atm pressure? We need a very low pressure to observe these cathode rays. Why we need those low pressures? Any idea? Any idea from you guys? Lamai, මොන හරි idea එකක් තියෙනවද why we need this kind of a very low pressure to see the cathode rays? No. Right. Let's discuss why we need a low pressure. It is like this. Lamai, pressure. Let's discuss a bit about the pressure concept of pressure. Yes, what is the equation? There's an equation to come up with the pressure. Anyone know the equation which gives the pressure? Pressure is equal to which over which? Pressure is equal to, yes, any idea? Pressure is equal to, yes, I'll draw it here. Yeah, pressure is equal to force over area. Force over area. Pressure is equal to force over area. Right now, you may have heard about this equation, right? So, how a pressure arises in a gas? How the pressure arises? How the pressure appears in a gas tube? It is because of the gas molecules inside the tube. Pressure appears in a gas tube because of gas molecules inside the tube, right? When they collide with the walls of the walls of the tube, when they collide walls of the tube, they will insert some pressure on those. When the gas molecules, those are moving here and there, when those gas molecules collide the walls of your tube, those will insert some force on those walls of the tube. So when the force is high, when you insert more force by these gas molecules, you come up with a greater pressure. So that is how a pressure arises in a in a tube like this. In any kind of a container, the pressure is due to this effect. When the gas molecules inside the container hit the container's walls, those will insert some force on those walls, and that divided by the area of the walls will give you the pressure. So you clearly see, when you have less gas molecules, very few gas molecules appearing, when you have very few gas molecules appearing, right, very few collisions with the walls of the container, very few collisions of gas molecules with the walls of the container, so that the force inserted by those gas molecules will be low, so that the pressure will be low. So very low pressure means inside your gas tube you are with only very few number of gas molecules. That is the idea. If the pressure is high, that means you have greater number of gas molecules inside your tube. So pressure is a measure of gas molecules inside your cathode ray tube. So here we are maintaining a very low pressure, Maintaining very low pressure means we are maintaining a very low number of gas molecules inside your tube. That is the idea. So, what happens if the pressure is high? That means, if the pressure is high, that means you have more number of gas molecules inside your tube. If the pressure is high, that means you are with greater number of gas molecules inside the tube, like this. You have very, very high number of gas molecules inside your tube. Then what will happen? If you have this amount of very high amount of gas molecules inside your tube, what will happen? See, what will happen? So, when these rays hit these molecules, those rays will stop at that place. So, the rays are not being able to go through the gas if more gas molecules are there, and if those are not helping to go through the tube. Right? If more gas molecules are there, if the tube is more crowded by the gas molecules, very crowded by the gas molecules, then the cathode rays are unable to go through that towards the positive terminal. Right? So we won't be able to observe the cathode rays in such a situation. That is what happens with a high pressure. With a high pressure, that means you are with more number of gas molecules inside the tube like this. So the tube is more crowded with the gas molecules, so that the cathode rays are unable to go through those gas molecules to come towards the positive terminal. So cathode rays won't appear in such a situation. Right? So it is very important to note that to observe cathode rays, the cathode ray tube should be with very limited number of gas molecules like this, very limited number of gas molecules, right? Number of gas molecules should be very limited so that they will provide a very clear pathway for cathode rays to go through the tube towards the positive terminal, right? Very few number of molecules are allowed to be inside the tube. That is why we say very low pressures are needed. Low pressures means very few number of gas molecules. High pressures means very high amount of gas molecules. Those won't, right, allow the cathode rays to go towards the positive terminal, right? So that is the idea. So it is very important to note that we need to maintain kind of a low pressure, very low pressure to observe these cathode rays, right? Those are very fundamental ideas, and those are two questions can be asked from this experimental setup, right? Yes, Lamai, do you have any questions about these two explanations? And if you have any, you can ask. No? Right. Then let's write this stuff. Let's write these things in your note, right? See? Let's go to the note. It says, during the mid 1800s, scientists began to study electrical discharge through a glass tube pumped almost empty air. This device was an invention of British chemist and physicist William Crookes and is called Crookes tube or cathode ray tube, right? That is all there in your tube, right? Then, this setup is also there, right? So you can write this thing, gas with very low pressure is there inside the tube. So you can write this one that is not mentioned in your tube, right? That is not mentioned in your note. So write this thing, gas with very low pressure, right? Okay, the high voltage, that things are there. Then write this stuff, right? Write this stuff, right, of observation of the cathode rays, right? Just write with me, right? When two electrodes are connected, when two electrodes are connected, when two electrodes are connected to a high voltage source, the heated negatively charged plate, comma, the heated negatively charged plate, comma, called the cathode, the heated negatively charged plate called the cathode, produced a write it in red color, Lamai, write it in red color, stream of invisible radiation. That is very important, Lamai. Remember, the cathode rays are invisible actually. Those are without colors. Cathode rays are colorless, right? Stream of invisible radiation in red color. Okay? Right. In the next line, just write this thing. In the next line, just write, this radiation emitted from the cathode, was given the name, this radiation emitted from the cathode was given the name within inverted commas, write it in red color, cathode rays was given the name cathode rays. Right now, was given the name cathode rays. Right. In the next line, as the next para, just write this thing. As the next para, just write, although although come to the red color and write, the cathode rays could not be seen, 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 although the cathode rays could not be seen. Come to the normal color, lamai. Come to the normal color. Their presence was detected. Their presence was detected. Their presence was detected. Their presence was detected. Because cathode rays cause come to the red color and write it in red color. Gases at low pressure to glow. Gases at low pressure to glow. Just like this, right? So gas molecules inside the tube will emit some light, some visible light radiation, green color radiation due to this process. When the cathode rays hit those gas molecules, the electrons will come to high energy level, and when those things come back to the lower energy levels, the excess energy, the absorbed energy will be re-emitted as visible radiation. That is how the cathode rays gives you some colors, right? Gases at low pressure to glow come to the normal color, and again with the red color, which made other substance to fluorescence, which made other substance to fluorescence, which made other substance to fluorescence. Fluorescence means give off light, they emit light. This is how the process is done, which made other substance to fluorescence, right? Okay, so you can draw this one. See, you can draw this one. The cathode rays are colorless, right? But with this process, this could be helium molecules at the gas, right? Helium molecules at the gas, or this could be some atoms of the walls of your container, walls of your glass tube. Atoms of walls of glass tube. Could be anything. That is how the cathode rays are able to be seen, right? Okay, just draw this stuff, right? Right, now cathode rays are colorless, right? They cause the gases at low pressure to glow, emit light. Gases at low pressure to fluorescence, emit light. Right? Okay. See, that is how cathode rays are able to be seen. Right, no? So we'll go to the next point, right? So you can write some quick note about this thing as well. I'm not going to give it to the note, but you can have a quick note about this thing. Why we need a gas with very low pressure, right? The idea is, right, low pressure means low number of gas molecules appearing inside tube, right? Low pressures means, you can put some arrow line like this. Low pressures means very low number of gas molecules inside tube, right? That means no resistance or no barrier, or we can say less barrier for movement of cathode rays towards the anode. Just put it like that. With the picture, you can underline very low pressure thing that is needed because of this. Very low pressures means low force will be applied on the walls. That is because of low number of gas molecules appearing inside the tube, right? So with low number of gas molecules appearing inside the tube, less barriers for movement of cathode rays towards the anode. It is easier for cathode rays now move through the gas. Less amount of gas molecules are appearing, right? No barriers that much. So that is very important to note that you have to maintain a very low pressure to observe cathode rays, right now. Okay, so that is done. Let's discuss about the properties of cathode rays now, right? Let's discuss about the properties of cathode rays. We have came across few properties, right, with the video as well, right? You have seen, you have heard about the three main properties. Cathode rays are traveling in straight lines, and the cathode rays are with some momentum, the kinetic energy, and the cathode rays are with a negatively charged nature. So let's discuss about those experimental observations leads to those conclusions, right? Okay, first thing, the cathode rays are actually traveling in straight lines, right? So let's come up with the experimental setup to prove to see that observation and examine the points there, right? Okay, so the cathode rays are actually traveling in straight lines. So the experimental setup, you need to come up with that observation is like this. So we have they have done some small changes to your cathode ray tube to observe the specific quality. To observe specific qualities of cathode rays, they will do some changes, some smaller changes to your cathode ray tube, right? Then only you would be able to see those specific observations, specific properties of cathode rays, right? So what they have done is, to observe that property of cathode rays traveling in straight lines. Yeah, that is the first property we are dealing with. Cathode rays travel in straight lines. Right, let's see how they have made the setup to observe this property. The cathode was there. They have applied some high voltage. The negative terminal is the cathode. Cathode was there, and as the anode, they came up with a metal cross like this. Came up with a opaque metal cross like this, kind of an opaque object. Metal cross is kind of an opaque object. Instead of the anode, they place the opaque object like this, right? This is your anode thing, right? This is your anode thing. So cathode, as the anode, they came up with a opaque metal cross, kind of an opaque object. as your anode, right? And these two terminals are connected to a very high voltage, right? High voltage. Then when they have constructed this kind of setup, they have seen, right? They have seen some shadow appearing at the end opposite to the cathode. At the end opposite to the cathode. This is the end of the cathode and this is the opposite end of the cathode. They have seen the shadow of the opaque object appearing, right? Shadow of the opaque object appearing, right? So they have seen that, right? This is the shadow of the opaque object or the shadow of the metal cross. Right? To see this thing, cathode rays should travel in straight lines. So as cathode rays are not going through this opaque object, right? Those cathode rays, when the cathode rays are not going through the opaque object, right? The cathode rays which came directly to the opaque object won't go through this thing, so that those guys won't be able to hit the places at the end opposite to the cathode. But the other cathode rays which were able to pass this opaque object will hit the places of here these things, so that is why the green color glowings appeared at these places. But the green color glowings are absent with this area, because those cathode rays came directly towards the cross, stopped at the metal cross, never went through that, so that you won't see any cathode rays come into this area. Those are the situations where when the cathode rays are coming directly to the cross. When the cathode rays which are able to pass the cross, right, came and hit the walls of these area, that is why you see some green color appearing with these areas. These areas are green colored because those areas are hit by the cathode rays, not this black color area, because the black color area, right, so those cathode rays coming directly to the cross won't be able to pass the cross, right? So that is why this space is black colored without the green glow. Black colored means without the green glow, right? That is how the shadow is appeared. So to have this kind of shadow, definitely cathode rays should travel in straight lines, right? If not, if cathode rays can go like this curved pathways, if cathode rays are able to go through curved pathways, then those rays will be able to come to these places as well, come to hit at these places as well. As cathode rays are not being able to go like this, right, like in curved pathways, those won't hit the places at these places. That is why the green color is not appearing there. That is why we see the shadow there, right? So that this proves that cathode rays are traveling in straight lines, right? Cathode rays are traveling in straight line. And this is with another kind of a conclusion. This observation gives you another kind of a conclusion. What was that? What is that? It is actually with this experimental setup and with this observation, we can say another thing. One thing is cathode rays travel in straight line. The other thing is we can say the cathode rays are emitting from the cathode. Cathode rays are emitting from the cathode. If the cathode rays are emitting from the anode, those rays will be able to come to these areas as well, these areas of the walls as well, the black area of the wall as well, right? So that those areas will also should have a green color glowing, right? So that is not what we see, because the cathode rays are not emitting from the anode. So we can conclude with this observation the cathode rays are emitting only from the cathode, right? So both of those observations, conclusions can be made with this observation of this setup, right? So quickly draw this one, Lamai. Quickly draw this setup. You should be able to come up with these setups, Lamai, for the first term test, right? Not for the O levels, it's not for the A levels, but for the first term test, they may ask such questions. Give a label diagram of the experimental setup which proves that cathode rays travel in straight lines. Such kind of question can be asked. Give a label diagram of the experimental setup which proves that the cathode rays are traveling in straight lines. If such a question is asked, you have to draw this thing with some labeling. These are the cathode rays, right? Just quickly draw this setup, Lamai. Cathode rays. Quickly draw this setup. Right, no. Okay. You can take a screen capture as well, Lamai. You can take a screen capture. Let's continue quickly. So for the pictures, just take a screen capture and then you can complete the note. No, even these pictures are there in your resource book as well. No, right. Quickly draw this one. I'll give you 1 to 2 minutes, right, to draw the pictures, right. And we'll share the we'll share the picture if you need it, right, at the end of the lesson, right. Take a picture. Okay, let's write this stuff, right. Let's write this small description about what we have discussed here, right. Okay. Now this is just like a normal physical class, Lamai. This is just like a normal physical class. We will provide you all the notes, complete notes, right? So so that nothing will be mixed, right? So all the things we are doing at the physical class will be done here, and the tutors will be provided to you to your doorsteps, right? So so we are writing the notes just like in physical classes, right? The most important stuff are writing, right? Not all the things, right? Okay, and we'll do some question sessions as well at the end of the session, right? Okay, so let's write the points here what we have discussed. Just go to this. When n write it in red color, opaque object means through that light won't travel, the opaque object, right? You know that stuff, right? When an opaque object come to the normal color, like a metal cross is placed in the path of cathode rays, when an opaque object like a metal cross is placed in the path of cathode rays, in a discharge tube, put a comma, come to your red color pen and write a shadow with sharp edges of metal cross. A shadow with sharp edges of metal cross. A shadow with sharp edges of metal cross. Come to the normal color, Lamai. Come to the normal color. Is formed at the end is formed at the end opposite to the cathode. A shadow with sharp edges of metal cross is formed at the end opposite to the cathode. That was the observation. Then let's write the conclusion. As the next para, come to the next para and write. The placement of the shadow proves that 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 put a comma and write, put some dashes and write lamai. First dash, under that first dash, write it in red color. Just write these two conclusions with the red color, right? Cathode rays emit from the cathode. Cathode rays emit from the cathode. If only the cathode rays are emitting from the cathode, you will see this kind of observation, right? If it is to emit from the anode, that is not the opposite, should be the case, right? So here, this proves that the cathode rays are emitting from the cathode. Cathode rays emit from the cathode. That is the first dash. Next dash, the next conclusion from this observation. Next dash, write it in red color again. Cathode rays travel in straight lines. Cathode rays travel in straight lines. Cathode rays travel in straight lines. Straight line motions are there. Cathode rays travel in straight lines. Right now? Okay. So those are the two conclusions we can make with this observation. Right. Okay. Let's come up with the second kind of property of cathode rays. Right. This second kind of experimental setup which we prepare to observe another kind of property, right, of cathode rays. See, number 2, we say cathode rays are beam of particles with some momentum, means kinetic energy and mass, right? So cathode rays, let's see, the second kind of property now we are going to discuss. Cathode rays are beam of particles having mass and kinetic energy. This is the second property we are going to discuss here, right? See, so what kind of changes should be done to your cathode ray tube to observe this property of the cathode rays? It is like this, Lama. You should be able to come up with the correct cathode ray tube, right? To come up with the required property, right? So to observe this property, having mass and kinetic energy, we construct the cathode ray tube a bit differently than to the earlier situations. It will be like this. You have the cathode here, you have your anode here, cathode is there, you have your anode there, right? The anode, which is your positive terminal, cathode, which is your negative terminal. You have both the cathode and the anode. And to observe this property, you need to come up with a light parallel wheel here. Light parallel wheel in the path of the cathode rays. In the path of the cathode rays, you have to place some light parallel wheel. This kind of experimental setup which you can come up with. Some other setup was mentioned in your video, but this is another kind of experimental setup you can think of. You can place light paddle wheel like this, light paddle wheel, which is able to rotate, right? So what will happen? This is your light paddle wheel, right? So what will happen? So what will happen? So you will see kind of observation. What is that observation? If you are to construct this kind of setup and apply some high voltage to this anode and cathode, you will see the rotation and some movement of this paddle wheel, right? This paddle wheel will rotate. This paddle wheel will rotate and move forward and move forward, rotate and move forward. That is what you will observe with this kind of a setup. So how come this paddle wheel is able to move like this, rotate and move? That is because of cathode rays transferring some kinetic energy to paddle wheel to move. The idea is this. So if the paddle wheel is able to move, that means your paddle wheel is gained some kinetic energy. Only after applying the voltage, the paddle wheel starts to move, right? If you are not applying the voltage, when the cathode rays are not seen, the paddle wheels not moving. But when the cathode rays are generating, the paddle wheel starts to move, right? That means paddle wheels are able to move when the kinetic energy is there with the paddle wheels. How come that paddle wheel gain some kinetic energy? Kinetic energy is the energy involving in movements, right? So paddle wheel is able to gain that kinetic energy actually by the cathode rays. The kinetic energies of the cathode rays actually transferred to the paddle wheel. The kinetic energies of the cathode rays actually transferred to the paddle wheel. That is how the paddle wheel gains some kinetic energy, and that is how it starts to rotate. Only when you have kinetic energy you can do some movements, right? So paddle wheel gains some kinetic energy with the cathode rays. So cathode rays are the ones which provided the kinetic energy to paddle wheels. So that to provide that kinetic energy to the paddle wheels, the cathode rays should have some kinetic energy. Cathode rays should have some kinetic energy, right? To provide some kinetic energy to the paddle wheels, to them to move, the cathode rays should have some kinetic energy. The kinetic energy is half mv squared. We all know the kinetic energy is half mv squared. So to have kinetic energy with the cathode rays, definitely it should have a mass and a velocity. Without a mass and a velocity, you can't possess any kind of a kinetic energy. So cathode rays are with a mass and a velocity, right? So we can say with this observation, right, cathode rays are particles. Having a mass means you are with a particle property. Mass, touchable situation, right? It's a particle property. So cathode rays are particles with mass and a kinetic energy. So to have a kinetic energy, as we need to have a mass and a velocity, one can say cathode rays are with some momentum as well. Why? Momentum is given by mv So, as cathode rays are with kinetic energies, the cathode rays are with mass and velocity. That means it is with a momentum as well. So that is how we say the cathode rays are with kinetic energies and mass as well as momentum, and those are kind of particles, beam of particles. Cathode rays are beam of particles. Having a mass means you are showing some particle properties, and having a mass and kinetic energy, and one can say those are with kind of momentum as well. You are with mass and velocity means you are with momentum, right? Okay, right, let's go to this, right? Let's draw the picture first of all, right? Quickly draw the picture, right? Then we can write the stuff we have discussed here. So light paddle wheel rotates actually, right? Okay. Let's write the things, right? This clear? Right. Let's write these things here, right? First point. With the picture, just write these ones. First point. On placing a 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 come to the red color, light paddle wheel on placing a, with the red color, just write light paddle wheel come to the normal color, in the path of cathode rays, light paddle wheel in the path of cathode rays, in a discharge tube, in the path of cathode rays in a discharge tube, on placing a light paddle wheel in the path of cathode rays in a discharge tube, put a comma and write it in red color again, the blades of the paddle will rotate, 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 the blades of the paddle will rotate. Next point. This was considered evidence that 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 come to the red color and write cathode rays have momentum, cathode rays have momentum, cathode rays have momentum. This was considered evidence that cathode rays have momentum. Right, no? Okay, cathode rays have momentum. Okay. In the next line, just write this. Come to the normal color and write. However, there is a doubt on this conclusion. There's a doubt on this conclusion. There's a doubt on this conclusion. There's a doubt on this conclusion as as, there's doubt on this conclusion as, come to the red color and write, heating of the tube can also make the paddles move. Heating of the tube can also make the paddles move. Heating of the tube can also make the paddles move. Heating of the tube can also make the paddles move. Right now? So let's discuss a bit about that idea. Yes, what I have earlier discussed is actually one conclusion scientists have made with this observation. But another bunch of scientists are arguing, that this rotation of the paddle wheel is not because of the cathode rays, but they are saying that is because of heating of the tube. That is because of heating of the tube. Right? Some scientists are arguing about the earlier conclusion. They are saying that this is not because of the cathode rays, it is because of the heating of the tube, the paddle wheel is rotating. That is also can be acceptable, Laman. That is also there in your resource book, right? And that is also acceptable. Why is that? Because we know when very high voltage is applied, some heat will be generated. So normally in such a situation, when some voltage is applied, some heat will be generated. You can clearly observe that thing with even your light bulbs. No? With light bulbs, right? You can observe that thing. No? The heat generation. That will happen. Right? So some heat will be generated at the cathode. Right? So some heat radiation will travel from here to here. Some heat radiation will travel from here to here. So that will also cause the paddles rotate. That will also cause the paddles rotate. So some scientists are arguing that rotation of paddle wheel is not because of the cathode rays, but because of the heat generated inside the cathode ray tube with this process. So such kind of idea is also there. Both the things are okay and both are accepted nowadays, right? So that is all about the second experimental setup, right? About the cathode rays, right? These things will be asked in your first term test paper, right? Let's come up with the third property. Before that, do you have any questions? Yes, Ahmad is still there with us, right? So, do you have any question about the two earlier discussions about the cathode rays? So, you can discuss things. No. Not yet. Okay. Right. Then we'll move to the next section. The third property. We'll discuss about the third property of cathode rays. Right. So we have done discuss about two properties with those experimental setups. Right. Let's come up with the third property of cathode rays. Right. Okay. So the third property, it says the cathode rays are negatively charged particles. Cathode rays are negatively charged particles, right? That is the third property we are going to discuss, right? Cathode rays are negatively charged particles. Let's see what kind of a setup we are supposed to produce to come up with that conclusion, right? This is the third property. cathode rays composed of negatively charged particles. Let's see what kind of a diagram we are supposed to come up with, right? What kind of setup? It is like this, Laman. So to prove this thing, we can come up with two experiments. We can use two experiments to prove this idea. The cathode rays are negatively charged particles. One is actually by applying an external electric field in the path of the cathode rays. In the path of the cathode rays, we can apply external electric field. See how the things are done. So you can come up with a anode here like this kind of anode. This is the experiment setup, leads to these observations. You can come up with anode here, right? Kind of anode with some tiny hole appearing there. Then you can apply kind of a external electric field, kind of external electric field. See, this is a kind of external electric field, another electric field, external electric field, right? This is your negative terminal, let's see. This is the positive terminal of the external electric field. External electric field. External electric field, right? What we are able to see with this kind of setup. So basically, cathode rays will come. I am concentrating on this specific cathode ray. Most of the cathode rays will come and hit the anodes and stop there. But the cathode rays coming directly towards the hole of the anode will be emitted from here and then will travel towards the positive terminal. Will travel towards the positive terminal of the external electric field. So this is the observation we are able to see. Cathode rays will deviate, will change their direction of movement towards the positive terminal of the external electric field. That is what happens. So these are cathode rays. Cathode rays will deviate towards the external electric field's positive terminal. Deviate towards the positive terminal of the external field. Right? So that we can conclude the cathode rays are negatively charged. Because if some particle is attracting towards the positive terminal, that means the particle should carry some opposite charge. If it is attracting to the positive terminal, this should carry the opposite charge, the negative charge. So cathode rays are negatively charged. That is how we conclude that, right? So if cathode rays are coming towards the positive terminal of the external field, we can say the cathode rays are with the opposite charge. That means negatively charged. Right? The cathode rays are negatively charged. Right? It is how we prove with the use of external electric field. The cathode rays are negatively charged particles. So with this field, with this kind of setup, one can argue why we need this kind of setup. Why we need this kind of setup to prove the cathode rays are negatively charged. One will argue that even this setup even this kind of a setup, right? Even the setup what we have earlier drawn, the Crookes setup, this is negative, this is positive, as cathode rays are starting from the negative terminal and going towards here. So even this kind of setup will be enough to prove the cathode rays are traveling towards the positive terminal කියලා කවුරුරි අහන්න පුළුවන්. One can ask like that. One can say that no need of this kind of heavy setup to prove this idea. To prove this idea that cathode rays are traveling towards the positive terminal, to prove this idea, we don't need this kind of setup. Even this setup proves that no, like that some kind of some may ask such a some may have such kind of idea that this is also enough to prove that the cathode rays are traveling towards the positive terminal. Why we need then the question is why we need this kind of setup. The question is why we need this kind of setup to prove that cathode rays are traveling towards the positive terminal. Why this is not enough? Why this setup is not enough to prove that cathode rays are traveling towards the positive terminal? Why this is not enough? See, any answer? Right? Why this setup is not enough to prove that cathode rays are traveling towards the positive terminal? Why we need this kind of a complex setup to prove the cathode rays are traveling towards the positive terminal? Any idea? Yes? Cathode rays travel in straight, cathode ray travels in straight line, so that if any object is to place here, that will travel toward that. The cathode ray will travel toward that. Yeah, the idea is correct. So it's like this now. The idea, the simple idea is this now. So you have a ball. Get this idea? You have a ball. You have a ball, and you put some force there. You put some force there to the ball. So ball is traveling here with this direction. Ball is traveling towards this side, this direction. Just travels. This is the flow. Ball is just traveling that direction. And what you do is you just put a bat here. You just put a bat here, and then you are saying that ball is traveling towards bat. You are saying that ball always travels towards bat. That is not good, no Lama. What you have done was the ball was traveling not towards the bat. What you have done was you just put a bat there, and now then you are saying that ball is traveling towards the bat. That is not good, no. If you have put the bat in a place like this, if you have put the bat in a place like this, which is not inside the path of the ball, then ball deviates its pathway and come towards the bat. Then you can only say, yes, ball is always coming towards the bat. That is the idea. When something is traveling by, if you put something in the pathway, right, then you can't say that at the initial point that ball decided to travel towards bat, right? That's not the idea. So if you need to confirm the idea that ball is traveling towards the bat, you have to put the bat in not in the pathway of the ball. If ball needs the bat, what ball will do is ball will deviate its pathway, change its pathway to come towards the bat. That is the idea. So that is why we say this setup is not enough. This setup is not enough to prove that cathode rays are traveling towards the positive terminal. You need to have a positive terminal not inside the pathway of the cathode rays. Then only, if cathode rays always prefers the positive terminal, then cathode rays will deviate, change their pathways to come towards the positive terminal. That is what happens. So that is what happens here. So that we can prove that cathode rays are traveling to the positive terminal only with this kind of setup, which is not good for such proving. Right now, that is the idea. So this setup will prove that cathode rays are traveling towards the positive terminal, so that the cathode rays should have the opposite charge, means the cathode rays are negatively charged. Right now, okay. So any question about the explanations? No. Are you clear? You guys are clear about the ideas, no? Right. Okay. Let's discuss the second method, the second experiment which can be done. Let's discuss the two methods, two things, and then we can write some notes, right? So let's discuss about the second experiment which can be done to prove that cathode rays are kind of negatively charged particles. Yes, the second experiment which we are able to do is actually this, right? I'll take some other pen. Right, you can complete this kind of experiment, right? Not only kind of an external electric field, but you can apply kind of a external magnetic field as well. You can come up with an external magnetic field as well to prove that the cathode rays are negatively charged. See what you should be done. To come up with that conclusion with the use of external magnetic field. Yes, the setup is again bit like the earlier situation, right? So you have the cathode and anode appearing like this. This is your cathode, and you have the anode as well, right? You have the anode here as well. See, this is your anode, right? So cathode rays will emit from the cathode and travels towards the anode. I am just concentrating on the specific cathode ray which is coming directly towards the tiny hole of the anode, right? Then you can place some external magnetic field here, some external magnetic field, right? Some external magnetic field, right? So this could be marked as the north pole and this as the south pole. This is kind of a external magnetic field, external magnetic field, right? Let's see what will happen if you apply this kind of external magnetic field to the path of the cathode rays. What will happen, Lamai? It will come like this, right? Till it feels the existence of the magnetic field. Till it feels the existence of magnetic field, it will come, and then it will deviate. Not towards any of the poles, but perpendicular to the field. It will deviate perpendicular to the field like this. Okay, perpendicular to the field. So keep it in mind, in an external electric field, the cathode rays deviate towards the positive terminal. But in an external magnetic field, it will deviate not towards any of the poles of the magnetic field, but perpendicular to the field. Right? Let's try to grab that idea more precisely. Actually, this deviation, this direction of deviation can be predicted with the use of Fleming's left hand rule. You may have heard about that in your O levels, Fleming's left hand rule. Yes, heard about the Fleming's left hand rule. Left hand rule neither done on it. Fleming's left hand rule, right? So we can apply the Fleming's left hand rule to this setup to come up with the direction of deflection. To come up with the direction of deflection of this cathode rays, we can apply the Fleming's left hand rule. Then we can come up with the direction of deflection. See, let's try to apply the Fleming's left hand rule, right? So left hand, take the left hand, right? And let's apply the left hand rule. So yes, this is your left hand, right? So what are the components here? You have the thumb, index finger and the middle finger, right? What are the components appear in this with this one? Yes. Okay. So yeah, let's take this one correctly. Okay. See, it is like this. I'll take this, right? Okay. Left hand. So three components are there. It is FBI, right? Force, magnetic field, direction of the magnetic field, and the I means the current flow direction, direction of the current flow, direction of the positive charge, right? Yeah, I'm going to apply this thing, right? Force, that is to where the particles will move. Particles will move to the direction of force applied. Particles will move to the direction of force applied. B, direction of magnetic field from north pole to south pole. I, current means actually the direction of current, direction of the positive charge, the movement of positive charge, current, right? Let's apply this one, right? Okay. See, these are cathode rays. Nowadays we know these are electrons. Nowadays we know these are electrons, negative particles. So direction of current flow should be like this. Direction of current flow should be like this, right? Direction of current flow should be like this, right? Because the negative particle movement is towards this. That means direction of the positive particle should be like this. Direction of the current is from positive terminal to negative terminal. Direction of the current flow is this, right? Current flow is this. B means magnetic field. Direction of magnetic field. Direction of magnetic field is from north to south, like this. North to south. Direction of the current flow is this. Negative particle movement is towards this side, means positive particle movement is this side. Direction of the current is towards this side. Magnetic field is towards this, north to south, so that you clearly see the force will be applied on those particles towards you. Force will be applied on these particles towards you. See, towards you. So the direction of movement is actually perpendicular to the field. This is the magnetic field. This is perpendicular. See, perpendicular to field, not towards any of the north or south poles. That is actually the direction of movement of negative particles. So that we can say the cathode rays are negatively charged, right? So remember that this direction of deflection is actually perpendicular to the magnetic field, right? So if you are to apply the magnetic field like this, if you draw some lines of the magnetic field appearing like this, right? So this thing, right, is with kind of that. So let's see, like this. its direction is perpendicular to the field, perpendicular magnetic field, right now. So that is how the cathode rays deviate in a magnetic field. So this is also a proof that cathode rays are negatively charged, right now. So let's come up with these two setups. Quickly draw these two setups. I'll give you some time, right? Few minutes, right? I'll give you 2-3 minutes. Just draw two of these setups, and when drawing the two setups, right, keep some space at this place. You can draw the two setups at the left hand corner of your space, and the right hand corner, let's leave the right hand corner to write the things, I mean explanations, right here. Let's go to the two setups here. So you can apply the left hand rule here, right? I'll do this one. These are cathode rays. Reflection is actually towards you or towards us. This is towards the positive terminal. No need of drawing this stuff, right? So here the deviation is towards the positive terminal, but here the deviation is not towards any of the poles, but deviation is perpendicular to the magnetic field. Perpendicular to the magnetic field. If you are done, Ahmed, put a thumbs up, right? Then we start writing. All right, no? Okay. Yeah, right. We'll let's write the note, right? These two things, right? First, with this setup, just write here, right? When n, write it in red color. Electric field applied, when n, electric field applied, come to the normal color. In the path of cathode rays, again come to red color and write, cathode rays deflect towards the positively charged plate, cathode rays deflect towards the positively charged plate. You can underline the word towards. With your blue color pen. Just underline the word towards. cathode rays deviate towards the positive charge plate, right? Next point with this setup, right? Just write it here, right? When a come to the red color and right, right? Magnetic field is applied. Come to the normal color and right. In the path of cathode rays, put a comma and write it in red color. Again, write it in red color. Cathode rays deflect perpendicular to the magnetic field. Cathode rays deflect perpendicular to the magnetic field. So, it will deflect perpendicular to the magnetic field. Right? Deflect perpendicular to the magnetic field. This field is there. Deflection is perpendicular to the field. Right? Okay. Come to the normal color and write. The direction of deflection is similar to the deflection of any other negatively charged particle. The direction of deflection is similar to the deflection of any other negatively charged particle. Right? Okay. Next point. That third point is common to both of the stuff, right? Next point, just write. Therefore, cathode rays can be considered as write it in red color, beam of negatively charged particles, in red color, write it in red color, beam of negatively charged particles. Right, no? Okay, that is about the three main experiments, right, which shows some three main properties of cathode rays. Lagi major properties, three main properties of cathode rays have been discussed with those setups, right? Okay, so when we are referring to A-level questions, the past paper questions, the MCQs, right? Actually, there is a book set called PSURU books, right? You can buy those PSURU books, right? In those books, right, the past paper A-level questions are categorized, and there. So with the cathode rays, all the questions came under cathode rays will be there in one section in those books, PSURU books, A-level books, right? So buy some, and we'll give you the tutor as well, right? The workbook, we'll provide you a workbook, and there are also the questions of all the section-wise questions will be there. The past paper questions are there. So, or else you can buy the PSURU books, right? Not that much; those are not that much costly. There are all the questions, all the MCQs, past paper MCQs are there. In our workbooks as well, we have put those questions. Anyway, when you study those questions, you will come across more properties of cathode rays, not only the 3 properties given in the resource book. In the resource book, they have mentioned about only 3 properties. No, they travel in straight lines and emits from the cathode. There is one property. The second thing is it is with some mass, kinetic energy as well as momentum. The third property is which we have discussed now. Those are kind of with beam of negatively charged particles. But other than those 3, some other properties are also questioned in A-level past papers. You will come across those, right? In your school papers, school term test papers also, you will come across few more properties. So that I have included those as well in our note. So let's go through those properties as well. Let's have some idea, because those will be there in your question papers, even though those are not there at the resource book. At the first lesson, inauguration lesson, I have told you that the resource book is the minimum you should know. Resource book is the minimum you should know. That is not the all. Resource book is not the all you should know. It is the minimum you should know. So you should know much more than the resource book, right? To have a good grade, to have a good decide score in your A levels. So to answer the questions which will be there in your school term test papers, even in A levels. So let's go to some of other properties which have been questioned in past paper A level papers, even in past school paper questions, right? Papers, right? Okay, let's examine few more properties of cathode rays, right? Okay. Name of the book you mentioned about the Pesuru books, right? So just go to a bookshop and ask for classified MCQs. Classified MCQs, right? So classified MCQs, right? So Pesuri is kind of a book, but some other books are also there, but this is the most common name, right? Even we will provide you the workbook, right? I'll provide you the workbook, then I'll put the workbook as well to the group after this class, right? So there are also you will come across all the questions asked from the first stuff, right? With the cathode rays and stuff, right? So there also you will see that. So some other books also there. Just go for and ask for a classified MCQs in A levels, right? Pesuri is one such kind of a book for all the physics, chemistry, even for biology. You have this kind of book set, right? For all the complete syllabus book set is there. It will cost like 1,500 or something, right? Not that much for all the complete syllabus, right? For all the MCQs, right? Classified, right? So Pesuri is one kind. Some other kinds will be there in your area, right? Just go for a bookshop and ask it, right? Okay, so let's right, and with our workbook as well, you should just do the questions, MCQs appearing at the workbook. I'll send that thing after the class. Then you will come across these properties as well, right? Those are past paper questions, right? Okay, see, we'll discuss few other properties of cathode rays, right? Yeah, place the books, right? Okay. A-level classified MCQs, right? Right. Okay. Right. Then we'll come across then other properties. Let's discuss one by one, which is there at our notebook, right? Property number 4. Property number 4 is that the cathode rays are emitting perpendicular to the cathode. The cathode rays are emitting perpendicular to the cathode. Emitting perpendicular to cathode, right? So actually that can be, they won't ask you to draw the diagram in this case, right? They won't ask you to draw the diagram in this case, right? But I always come up with some logical reasonings. No? So this is the setup we prepare to show that cathode rays are emitting from the emitting perpendicular to the cathode, right? So this could be your anode, and this could be your cathode, right? So you should apply some high voltage with a low vacuum situation, right? So if you are to apply this kind of a setup, come up with this kind of setup, the specialty here is actually your cathode here is kind of a, right, concave cathode, kind of a concave cathode. Concave cathode means, yeah, it is kind of a this, it is not a normal cathode, it's a concave cathode. You may have come across the concave mirrors as well, right, in your light lesson, in your small ages, concave mirrors, right? So it's a concave cathode. So if you are to construct this kind of setup, you would observe that there is a point which is actually the focus of this concave cathode, right? All the cathode rays are traveling by. At some single through some single point, all the cathode rays are traveling through that point. Actually, that is the focus of the concave cathode. This actually proves that the cathode rays emit perpendicular to the cathode. Cathode rays emit perpendicular to the cathode, right? So this concept comes up with light even, as light rays are emitting perpendicular to the mirror, right? Those are traveling through the focus now. That idea is applied here as well. So cathode rays are generating perpendicular to the cathode. This is the experiment setup that proved that idea, right? No need of knowing the setup, those that won't be asked, but you should know this point here. Cathode rays emit perpendicular to the cathode, right? Okay, that is the fourth idea. Fifth, let's go to the points quickly, the few points which is not appearing in the resource book, right, but will be asked in the questions, right? The fifth point mentioned in the note is actually those are colorless. That is, we know, right? The cathode rays are colorless. Colorless. Those are colorless and invisible. So that invisible, without a color means we can't see those things, no? Invisible. So cathode rays are colorless and invisible. So that is something what we know, colorless and invisible. And we are able to observe the presence of cathode rays. We are able to observe the presence of cathode rays because of they are able to, right, give off light from the scintillating material, right? They are able to give off light from the scintillating material. That is how we observe the presence of cathode rays. Not because of they are colored, but they are able to do so, right? Okay, right? That is also some known stuff, right? Sixth property of cathode rays. See what they are saying. Cathode rays can ionize gases. Cathode rays can ionize gases. Can ionize gases. These are some properties of cathode rays. Cathode rays can ionize gases. How come? The idea is very clear. So to ionize gases, to ionize atoms as well. So if you are to think of helium atom, helium gas, Helium gas is with helium atoms. So if you need to ionize that helium gas, means helium atoms, you need to provide the ionization energy required. To ionize kind of a gas, you need to provide its ionization energy. At least you have to provide the ionization energy. Ionization energy means the minimum energy needed to supply to eject an electron from the gaseous molecule, right? That is the ionization energy, right? So you need to supply the ionization energy to ionize a gas atom, gaseous atom, right? So cathode rays can provide that energy. Cathode rays can provide that energy. Earlier we had seen the helium. So gases are with these kind of energy levels. So the energy of the kinetic energy of the cathode rays can be provided to electrons appearing in those atoms. See, these are atoms, gaseous atoms. Gaseous atoms. You can provide the energy of the cathode rays. See, you have cathode rays. Cathode rays comes up with some kinetic energies. Cathode rays comes up with some kinetic energies. Those kinetic energies can be provided to these electrons by absorbing that kinetic energy. These electrons will eject out from that, so that cathode rays are able to ionize gases. Cathode rays are able to ionize gases. If the kinetic energy is enough to provide the ionization energy of the gas, those electrons will absorb those kinetic energies and eject out from the atom. So cathode rays are able to ionize gases. Cathode rays are able to provide the ionization energy needed. That means the minimum energy needed to eject an electron from gaseous atoms. So they can ionize gases. Helium, neon kind of gases can be ionized by cathode rays, as those are with some kinetic energies. That energy can be provided to eject the electrons from gaseous atoms, right? Okay, next point. Number 7, the properties of cathode rays. Actually, this property, the ionizing gases, this property is actually used when we are discussing about those positive rays. If you have come across the positive rays, which will be discussed at the next class, we'll discuss the positive rays concept at the next class, right? There also we'll study about this thing. Actually, cathode rays are able to ionize gases. That will be helpful, which will be very helpful to produce the positive rays as well. With the positive rays concepts, we'll come across this thing again, right? So remember that the cathode rays are able to produce positive particles out from gases. So those are able to ionize gases, right? Okay. Next one, number 7. Cathode rays can penetrate through aluminium foil. Cathode rays can penetrate through aluminium foil. Cathode rays can penetrate through aluminium foil, right? So that is there. Cathode rays can penetrate through aluminium foils. So if such a statement was there in your MCQs, there are some MCQs in your paper, right? You have to choose whether the statement is true or false. So in MCQ paper, there are some MCQs which you need to choose whether the statement is true or false, right? So if such a statement appears in such a question, if a statement appears like the cathode rays can penetrate through thin aluminium foils, that statement is true. That statement is true. Cathode rays can penetrate through thin aluminium foils, that statement is true. Right? Okay. So penetrate, you know the meaning of penetration, right? Penetrate means you can go through the material. The cathode rays are able to go through the thin aluminium foils. If you take some thin aluminium foil. So cathode rays are able to go through that. Remember, keep it in mind, this should be a thin one, thin aluminium foil. So through very few atomic layers, the cathode rays are able to go through. The reason is cathode rays are very small, right? If you are very small, you can go through some material. The spaces inside, through the spaces in your material, you can go through if you are very small, right? So go through the aluminium foil, right? The aluminium foil, you have the aluminium atoms like this, no? So to go through that, through the spaces of that, right, you should be a very small particle. So as the cathode rays are, we know the electrons, no? So those are very small particles, right? So those are able to go through these very small spaces available in solid stuff. We know in solids the particles are very closely attached, right? So through those very small spaces, cathode rays are able to go through, as cathode rays are very small, right? So cathode rays are able to go through very thin aluminium foils, very few atomic layers, thin, right? Okay, that statement should be known. Then there could be a question like this. See, tell me. First, clearly hear this statement, and I need your comment. Whether this is true or false. I need your comment whether this is true or false for this statement, this new statement. Let's hear that first of all, right? If there is a statement like this, cathode rays are with high penetrating power. Cathode rays are with high penetrating power, or penetration ability of cathode rays are very high. If such a statement appears, what is your comment? Is that statement true or false? Is that statement true or false? Yes, cathode rays can go through the thin aluminium foils. That is true. But if a statement was there like that, such statements are there, right? When you do the past paper MCQs, you will find those. Cathode rays are with high penetrating power. Cathode rays are with high penetrating power. Cathode rays are with high penetrating ability. What is your idea? Is that true or false? What do you say, Ahmed? Sorry? False. It's false. It's false. Why is that? Give me some reason that this is why I am saying that it's false like that. Why? Yeah, through the thin aluminium foil, but I know you have the idea, but the best example you can give that cathode rays are not able to travel through all the metals is your opaque metal cross. The opaque metal cross you have used in the first experiment. When you are to confirm that cathode rays are traveling in straight lines, you used kind of an opaque metal cross at the pathway of the cathode rays. So cathode rays were unable to go through that metal cross. If those were able to go through that metal cross, you won't see the appearance of the shadow. But the shadow was seen because cathode rays were unable to go through the opaque metal cross. So cathode rays are not able to go through all the metals and all the things, right? So very thin aluminium foil is okay, but not all the other metals, right? So that means cathode, their penetrating power is not that much high, right? It is with very some kind of penetrating power. Cathode rays are with some kind of penetrating power than the other larger particles, because cathode rays are very small, so that it is with some penetrating power, but that is not at the higher value, not at a higher value, right? Just some penetrating power, but the penetrating power is very high is kind of a false statement, right? No? I think you grab the idea, right? Okay, so such kind of a thing will be there in statement questions. Number 8, about the cathode ray stuff, right? Number 8, its velocity. Velocity of cathode rays is less than that of light. Velocity of cathode rays is less than that of light. Velocity of cathode rays. cathode rays, the velocity of cathode rays is less than that of speed of light. The speed of light is actually 3 into 10 to the power 8 ms minus 1. The velocity of cathode rays is less than the speed of light, right? The idea is this, Lama. So basically, right, any particle other than light particle, other than the photon, light photon, other than light photon, any particle, right, when considering any particle, their speeds are less than that of speed of light. Their speeds are less than the speed of light. When the particle is with greater mass, it's all about the kinetic energy, right? It's all about the kinetic energy, right? So when the mass, let's take the energy as a constant, right? When the mass is high, your maximum speed drops. When the mass is high, your maximum speed drops. That is the idea. So for any particle with a mass, can't have the maximum speed available in your universe. In our universe, the maximum speed available in universe, maximum speed available is the speed of light, 2.998 into 10 to the power 8. So you can say it as 3 into 10 to the power 8. Actually, with this speed, only the light photons travels. Photons are the only particles, actually light particles, travels with the speed of light. So with photons, their mass is equal to 0. With photons, the mass is equal to 0. This is just kind of an imaginary concept, right? Photon is kind of an imaginary concept. The Einstein said there's kind of a photons appearing. Photons means the light particles, the electromagnetic radiation, those energy particles, energy packets, right? So photons are with m0. So those are able to come up with the maximum speed, which is the speed of light. When the mass increases, the speed drops, so that the maximum speed of cathode rays is less than the speed of light. As cathode rays are with some mass, particular nature is there, so their maximum speed is less than the speed of light. So even though we have learned the stuff like this, we learned that maximum speed of cathode rays is less than the speed of light. That is what we are learning here. But in your A-level paper, in your A-level question, there could be a question like, this could be a statement like, the maximum speed of protons are less than speed of light. Such kind of statement will be there. That is the A-level situation. Not only the stuff which we have written in the book will be asked, like in O-levels. In O-levels, always the questions are asked from the book itself, textbook itself. But that is not the case in A-levels. They will ask more than that. In A-levels, actually what they are asking is the application, not the theory. Theory is there at the book. So in O-levels, they just ask the theory, the theoretical stuff, which were there at the book. But in A-levels, they will ask you the application. So you should know the fundamentals of those observations to come up with a new application, to answer properly to a new application. Right? That is what we expect in A-levels. So we teach you that cathode rays travel with less than the speed of light. The speed of cathode rays are less than the speed of light. That is what we teach you. But there could be a question in your paper mentioning that the protons, mentioning this kind of statement will be there. A proton, the speed of protons are less than speed of light. The speed of photons are less than speed of light. Such a question will be appeared. So that you should be able to answer, you should be able to choose whether it is true or false. Speed of photons are less than speed of protons. Proton, the positive particle in your atom. Speed of protons. Speed of protons. Protons, not the photons. Just protons. Speed of protons are less than the speed of light. If such a statement appears, you should be able to confidently answer those things. That is true. The statement is true. This is the theory. This is the theory. For any particle carrying a mass, for any particle with a mass than the photon, definitely should have a velocity less than the photon. For any particle with a mass, then that means should have a velocity speed less than the photons. Maximum speed less than the photons. That is the idea. So photon, neutron, helium atom, neon atom, oxygen molecules. The maximum speed associated with all of those guys are less than the speed of light. Not only that is true with the cathode rays, but also with all the other material particles. Right, no? That is the idea we should gather from the point number 8. Right? Okay. Any questions regarding those things? No. Right. Okay. Let's come up with the question, statement number 9. Statement number 9. Right? Ninth statement. Statement number 9. Right? 9. What it says? It says X-rays could be generated after the collision of cathode rays with a metal target. Right? So cathode rays can produce X-rays, can be used to produce X-rays. Produce X-rays. Can be used to produce X-rays. Right now, that is the ninth property. Cathode rays can be used to produce X-rays. Right? See, that can be also happen, no lamai. If cathode rays are able to produce light rays from gases or from the atoms at the balls of the glass tube, if the cathode rays are able to produce light rays, the green color electromagnetic radiation from those, why can't they produce X-rays? If the visible radiations are able to produce, definitely they can produce X-rays as well. X-rays is another kind of electromagnetic radiation like visible rays. So cathode rays can be used to do so as well. So if that is done by like this, like the earlier case, so when the cathode rays hit kind of metals like tungsten, those are the normal metals which used to produce the X-rays. When cathode rays hit those metals like tungsten, their kinetic energies will be absorbed by the electrons of tungsten. Normally tungsten metal do this activity. Tungsten, that is the metal which used to produce X-rays. The tungsten metal, when cathode rays hit those tungsten metal, the atoms in tungsten, the electrons inside the atoms of tungsten will absorb that energy and go to higher energy levels. When those things come to the lower energy level, the excess energy will be released as a X-ray, kind of a electromagnetic radiation. So it is very true, cathode rays are able to produce X-rays, right, from metals like tungsten, right? So it can be used to produce X-rays as well. The same process, right? The same process which leads to ionization, same process which leads to give you the green colored light from gas particles as well as from atoms of the walls of the glass tube or scintillating materials, right? So you can produce X-rays as well if you are to direct some cathode rays to tungsten metal, right? Okay, so that is the ninth property. Okay, these are some other important properties associated with the cathode rays, right? Then we'll discuss the 10th property. The 10th one is very important and that is mentioned in the resource book as well. Let's come up with the next property, right, of cathode rays. First we'll erase this stuff now to discuss about the 10th very important property. Right. See, what are the other major properties of cathode rays? Right, property number 10. Let's discuss the property number 10. Right, property number 10 is with the cathode rays. It is this. This is very important stuff. Right, very important stuff. Right, you can write this thing. And then we'll discuss. First write the stuff, then we will discuss the property. Right, write it in red color. The property number 10. Right. See, the ratio of charge to mass, the ratio of charge to mass normally we denote it as EOM ratio. E means the charge, the simplest charge, over the mass, charge to mass ratio. The ratio of charge to mass of cathode ray particles observed from different gases or obtained from different gases was found to be the same. This is the property number 10. That is a very important property with the cathode rays. This observation was first done by the J.J. Thomson. He's a scientist, first observed this characteristic of cathode rays. And he have came up with the value as well for this thing. He had came up with a value for this ratio as well. That value is 1.76 into 10 power 8 coulombs per gram. This is the value he came up with. Okay, so let's discuss a bit more about this thing. This is a very important property with the cathode rays. This is there at the resource book, right? So you should know. Everyone should know about this thing, right? First of all, let's discuss how the Thomson is able to come up with this observation. How the Thomson was able to come up with this observation. Let's discuss a bit about this. The idea is this, Laman. The experiment was this. Thomson came up with a experiment setup like this. just the experiment setup which he used to confirm that cathode rays are with negatively charged particles, right? So this is your cathode, this is your cathode, this is your anode, right? So this is just the setup which we earlier used to explain the cathode rays are with positively charged particles, right? The same setup, right? So came up with some this thing, right? The external field, right? And cathode rays were deviated, no? Cathode rays were deviated to the positive plate, no? So actually what Thomson did was this. Thomson, right, carried out the experiment like this and took the deviation angle here. Right? I put it as a theta. Theta is a deviation angle. That is the angle of deviation from the original pathway for the cathode rays. Deviation angle. This theta is deviation angle. Deviation angle theta. And the other fact is this deviation angle theta is actually proportional to the charge over mass ratio. This deviation angle is actually proportional to the charge over mass ratio. That is very clear, Laman. That is very clear. Why is that? See, if you are, let's say, don't think of a cathode ray. Just think of any particle. Just think of any particle coming like this. Just think of any particle coming with this pathway. If the charge of that particle is high, let's see any particle, right? If the charge of this particle is high, if the negative charge of this particle is high, that will be greatly attracted. That will be greatly attracted to the positive terminal. Even from far away, it starts to get attracted to the negative terminal if the charge is high. If the charge of this particle is high, even from far away, it will attract towards the positive terminal. So the theta angle will be high. Theta angle will be high. So when the charge is high, theta angle will be high. So this deviation angle is proportional to the charge over mass ratio. That is what we are explaining here. When the mass is high, the opposite. Mass is high means when you have a higher mass, you are not that much keen to change your movement, which is known as the inertia. When the mass is high, you are not keen to change your movement. The movement, it may be the direction or the speed. The movement won't be keenly changed if the mass is high. So, if the mass is high, you won't deviate like this. The deviation will be smaller than like this. Deviation will be smaller than the situation. Deviation will be smaller than this if the mass is high. Less deviation because you are not keen to change your movement. You are not keen to change your movement. Change your movements, right? So that when the mass is high, the deviation angle will be low. See? So the deviation angle and the mass is with the inverse relationship. So actual charge to mass ratio is related to the deviation angle of the rays. So that what Thomson observed is with all the gases, like if you are to apply helium gas inside a tube, you get this deviation angle. If you change the gas to neon, still you get the earlier deviation angle. If you change the gas to O2, if you change the gas to N2, if you change the gas to any other Cl2, all the situations you get the same deviation angle. Same path the cathode rays took with all the gases. So deviation angle is same. The deviation angle is same means the E over M ratio is same. The charge to mass ratio is same. That is how Thomson concluded that E over M ratio of all the cathode rays producing with different gases is the same. That is the idea. The ratio of charge to mass of cathode rays of any particles obtained from different gases was found to be the same. He came up with this idea by the observation of the deviation angle. You always got the same deviation angle with all the gases inside the tube. That is the idea, right? So ultimately, by a calculation, with the calculation you are using the theta, he came up with this value. With a longer calculation involving theta, deviation angle, he came up with ultimate result for the E over M ratio. Right? Remember here, note that here, that Thomson was unable to come up with the charge and the mass of the electron. Thomson was unable to come up with the mass and the charge of the cathode rays. What he had found was the E over M ratio. Just the E over M ratio. Right? Actually, that was done by the calculation of deviation angles, right? Okay. Always you got the same deviation angle. That is the idea, right? So you can come up with this few little extra setup as well, right? Okay. The specialty here is, we'll discuss it the next point. The special thing we'll discuss in the next point. Thomson was able to prove that even with different cathodes, not only with the different gases in the tube, even with different cathodes, even with different metals as cathode, still you observe the same EOM ratio, same deviation angle. Thomson had carried out the same experiment with the use of different cathodes as well at the next time around. Earlier he has done the experiment using different gases inside the tube. You got the same deviation angle. Then he had run the experiment using different metals as your cathode. Aluminium, different metals, copper, zinc, different metals as cathode. Still you got the same deviation angle. That means still you are getting the same charge over mass ratio. Right? That is another special observation with this one. Just write that thing also and then we'll continue. Right? Point number 11. Just write the stuff. Point number 11. Right? Let's write. See, the nature of the cathode rays does not depend on. The nature of the cathode rays does not depend on. The nature of the cathode rays does not depend on. The nature of the cathode rays does not depend on. You can highlight the phrase does not depend on. Does not depend on. Roman number 1. Nature of the gas taken in the discharge tube. Roman number 1. Nature of the gas taken in the discharge tube. Roman number 1. Nature of the gas taken in the discharge tube. Just write it in red color. nature of the gas taken in the discharge tube, nature of the gas taken in the discharge tube. Roman number 2, the material of the cathode. Roman number 2, the material of the cathode. The material of the cathode. See, with different cathodic metals, with different gases inside the tube, still you got the same deviation angle. That means the EOM ratio is the same. That means same cathode rays are producing from each and every material, from each and every material, from each and every solids, from each and every solid, from each and every gas in the tube. You just produce the same cathode rays, same cathode rays. That is what we can conclude with the observation of same deviation angle, the same EOM ratio with those cathode rays. So with each and every metal, with each and every gas in the tube, you produce same cathode rays. That is how Thomson concluded the electron. That is how Thomson concluded that these cathode rays are the fundamental charge carriers. These cathode rays are the fundamental charge carriers appearing at the matter, appearing inside the matter. Right? So when we are considering the solid matter, gas matter, with all the matter, you get the same charge carrier, same cathode rays appearing. That means cathode rays should be the fundamental charge carrier, which is common to each and every matter. With each and every matter you are producing cathode rays, right? That means that should be the fundamental charge carrier which is there at all the matter, right? That was the Thomson's conclusion, and that is the instance where the Thomson was able to find the electron. With that conclusion, with that observations, Thomson finalized that these cathode rays should be the fundamental charge carrier, which was earlier said by the Stoney. The fundamental charge carrier, the indivisible, uncuttable, tiniest charge particle which is inside matter. That should be the electrons. So cathode rays are the electrons. That is confirmed by the Thomson in this manner, right? That is there in your resource book, in your book, right? Let's at the page number 7. Just complete the note, Lamai. Here it says, from those 10 and 11 findings, J.J. Thomson concluded that put this Roman number 1 and 2. That is the end of the note, right? Just put the 1 and 2. Roman number 1, just write. Cathode rays generated from all the matter contain cathode rays generated from all the matter contain a beam of negatively charged particles which are identical. That is the idea. From all the metals, from all the gases, you produce the same cathode rays. Contain a beam of negatively charged particles which are identical. Roman number 2, these are Thomson's conclusions, right? On this experiment, right? Roman number 2, these come to the red color and write. Identical charge particles should be common for each and every matter. Right? Okay? Right. So that is the end of the note today, right? And that is how Thomson was able to confirm the electron, the fundamental charge carrier of matter, the tiniest, indivisible, uncuttable unit of charge of matter. That is how Thomson was able to confirm that the cathode rays are the electrons, right? Okay, so that is the story of the electron, right? Ultimately, your Robert Millikan came up with the charge of the electron. Robert Millikan came up with the charge of the electron as 1.602 into 10 to the power minus 19 coulombs. That is the charge of the electron. That was done by his experiment of oil drop experiment. The Millikan was able to come up with the charge of the electron as 1.602 into 10 to the power minus 19 coulombs, right? With the charge of the electron and the EOM ratio, right? They were able to come up with the mass of the electron, right? So those are the fundamental stuff regarding the electron, right now? Right. So with this, we'll conclude the lesson for today, right? That was all about the electron. That today our topic was meeting the electron, right? So we had discussed all the scenarios happened, right, when finding the electron, right? So do you have any questions, Daru? Do you have any questions? So you can ask. If not, we can leave from here. Yes. Any questions, Hamad? No, right, okay. So clear, no? Right, so then we'll stop from here. So I'll send the workbook to the group as well, right? Then we'll meet from the next week then onwards. Goodbye then. Good night.